Hello and welcome to transformations of polynomial functions. So first, it's important to understand what each variable does in a transformed function. So first with a, there's vertical reflection if a is negative. If the absolute value of a is greater than 1, there's a vertical stretch. If the absolute value of a is less than 1, there's vertical compression. There's a horizontal reflection if it's negative. If the absolute value of k is greater than 1, then it's a vertical compression. If the absolute value of k is less than 1, it's a vertical stretch. Next, we have d. D shifts the graph horizontally. A hint is that you want to solve for x when trying to get the value of d, as in the equation it's negative. For c, it shifts the graph vertically. So here's an example of a transformed function that I chose. It has a clear value for every variable. So looking at this too, we can clearly see that there is a vertical stretch. With the 3 over here, we can clearly see that it's a vertical compression of 3. The value of negative d is negative 4, meaning that the value of d is 4, meaning that the graph is shifted 4 units right. And we can see that the c has a value of 5, meaning to shift the graph 5 units up. In order to graph a transformed function, you must have some coordinates of the parent function to transform. Since our equation has an exponent of 3, our parent function is going to be f of x equals x cubed, which is x to the power of 3. So I just choose some random coordinates: negative 2 and negative 8, negative 1 and negative 1, 0, 0, 1, 1, 2, and 8. You can get these numbers by plugging the x into the equation, which is just x cubed. And basically what you do in order to get the transformed coordinates is that for the x values, you must divide it by the value of k and add it by the value of d. For the y values, you must multiply it by the value of a and add by the value of c. So if you were to plug negative 2 into this equation over here, you would get 3.33. If you were to plug negative 1, you'd get 3.67, and you pretty much get the point of where I got all these numbers from. For y, you just plug in the y values into the equation. 2 times negative 8 plus 5 is negative 11. Negative 1 times 2 plus 5 is 3, and that's how I got all of these coordinates. If you were to use a graphing tool like Desmos, you could find how the graph actually looks, and using these graphs, we can confirm whether our coordinates are right. Just looking at both of them and the coordinates, we can tell that this graph was shifted 4 units to the right and 5 units up. It was stretched vertically by a factor of 2, and there was horizontal compression by a factor of 3. So how is this applied in real life? In sound engineering, audio waves are often modeled using polynomials and transformations that affect sound equalization and pitch correction. By looking at this picture, you can kind of get a hint of what I mean. Next, in computer graphics and animation, scaling, stretching, and shifting polynomials are key in rendering smooth curves, game physics, and designing animations. And lastly, in physics and engineering, polynomial equations help model things like the motion of objects under gravity, structural designs, and electrical circuits. An example is the quadratic transformation, which models how a bridge bends under weight. So hopefully now you have a better understanding of how transformations of a polynomial function work and know how they apply to real life.